In this video, we're going to be looking at the microscopic view of current and charge movement in a circuit or circuit element. We'll probably use mostly a wire to think about it, but we want to understand what's actually happening when you flip a switch, when you connect a battery, when things start to move. And this is all about Ohm's law still, but it's no longer at the circuit or even circuit element level. It's at a much smaller scale. So here's the concept. Right? If you imagine giving a soccer ball a series of random kicks in random direction, like this, right? You might kick it and then kick it and so on. And you've probably sort of encountered the random walk idea in math at some point. And so if you were to do this, right, the displacement of the ball, if you do it randomly, completely randomly over a given time, it would just be zero. It would always come back to the same spot. Now, if you do the same series of kicks, right, but it ends up being like this. We see some curved lines. It's not actually traveling straight all the time. You might ask yourself, well, what's happening, right? Why does it end up in a different position, right? What could be causing this? Now, if you're imagining kicking a ball on a soccer field, right, probably the most obvious thing would be that the field is actually sloping to the right. And so the kick direction is not all that's influencing its motion. And so a similar thing can help us think about what's going on inside of a wire, right? When you turn on a switch and there's a light attached to it, the light comes on immediately. And so that could lead us to ask the question, what about how fast the actual electrons, the charged particles, move inside the wire? Are they moving at the speed of light? So they're at the switch and they get over to the light so fast you can't even notice, or is something else going on? And then if wires change, right? Some wires are thinner, some are thicker. Does this actually affect the speed of the wires? Do they speed up? Do they slow down? What's happening? So there are two kind of possibilities, and we're going to use an analogy of cars driving down a highway to help us think about this, right? If the current was, instead of coulombs per second or amps, let's say it was some number of cars per hour. We'll go with 6, right? Which is not actually that many, right? If you were to stand outside and count cars and there were only 6 coming by a road an hour, you would say that's a pretty low traffic road. So if you wanted an even spacing of cars throughout the hour, right, if they were all 10 miles apart and traveling 60 miles an hour, quite fast, right, you would see 6 of them in an hour come by. On the other hand, you could have 6 cars that only go 1 car length in an hour, right? They're going very, very slow. So if you're looking straight ahead and counting, does it pass this line, right? And you can only count it once the whole car has passed, right? They start just on one side of the line, and it takes a whole hour for those 6 cars to cross the line. But the total car current is the same, right? The same number of cars cross that line in an hour. So very different scenarios. One is very spaced out, but traveling very, very fast, one after another. Another one is 6 cars moving very, very slowly, all in parallel with each other, crossing that line. Do either of these tell us exactly how fast an electron is going? Well, not exactly, but it gets at the idea that the actual motion of the electron is not as important or is not as directly related to the current as we might have thought, right? So electrons actually have 2 velocities we care about, and we call these conduction electrons. They're the ones that are available to be moving around in a metal, in a conductor, to conduct electricity. Certainly some of them are more tightly bound to the molecules and can't do this. But there's a very high random velocity. This is like the soccer ball kick, it's bouncing around. Even when there's no current, we find that in a metal, around 10 to the 6 meters per second is how fast an electron is moving, and a conduction electron is moving at any given moment on average, speed-wise. The speed of the current itself, which ends up being really, really low. This is how fast an electron actually moves through the circuit. We call this the drift speed, V subscript drift sometimes, and it ends up being a really, really low speed. This is much more like 6 cars in parallel. And because if you think about it, a wire's cross-section, even of a millimeter squared in area or something, is massive compared to an electron. There are 10 to the whatever electrons moving, so they don't actually have to move that fast along the wire to get that current. So here's a little video that I thought I would share with you that someone put together. You can follow the link and all the details. But right, you turn on a switch and the light comes on. turn off the switch, the light goes off, right? That's the idea. This is sort of what's going on inside of the metal while this is happening, right? The electrons are bouncing around fast, bouncing off the positively charged lattice. Then you turn it on and an electric field is formed. The electrons start moving across, right? This is still an exaggeration. They're moving relatively fast, but compared to their zipping around speed, it's actually not all that fast. And then you turn off the electron. So here's a tracking one electron, right? One electron bouncing around, when there is nothing going on in there, it's not really moving. Then we turn on the field, and now their general trend is much more to the right. And that's what we're really dealing with here. So here's what it looks like. We got a lot of bouncing around, very exciting, lots and lots of fun. And then we've got, A is here, B is here, right? With and without the electrons. So, A to B is just random. A to B prime is when the electric field is on. So it causes it to drift a little bit to the right from what it would do otherwise. So the rapid random motion is always happening. Doesn't matter about the current. The electric field, which we create by putting a voltage across a wire, causes it to drift in one direction, right? And this electric field is kind of like, it's caused by basically having a slope in the field, is a way of thinking about it. So how fast is the drift speed? Can we actually get into this and calculate this? Well, if we think about current as charge over time, we know that a section of conducting wire has some amount of current. Maybe we measure its length and we know its cross-sectional area. So the drift speed would be the length over the time it takes for an electron to move across it, right? If we could measure that. Well, we can't directly measure that, but what we can do is say, well, there's some number of conduction electrons per cubic meter. And this is actually something that you can kind of look up in a table about materials, probably in your chemistry textbook. It probably had this information in it. And then E is the charge of an electron. And Q is the mobile charge in this section of wire. How much of the charge is actually moving? So that Q is the volume of the wire times the number of charge electrons per conduction electrons per cubic meter, right? And then multiplied by the charge of each of those electrons, right? That's how we would figure out how much charge Q there is. And then the amount of time it takes to get across would be the last piece of this. So we've got area times length. So that gives us our charge. And we can say divide all that by time, but then what is length over time? That's the drift speed. We can say that current is equal to the conduction electrons per volume times electron charge times cross-sectional area times drift speed. And that's on your AP equation sheet for when you need to use it. And so our drift speed then is the rearranging of that. It's the current divided by n, that number of conduction electrons per volume times the electron charge times the cross-sectional area. And that's the drift speed. So the bigger the wire, the smaller the drift speed needs to be, because it's more like more lanes of cars moving very, very slowly. The more narrow the wire, the faster the drift speed, and so on. And you can see that relationship. Obviously, as the current goes up, the drift speed goes up. But it's not the most dominant factor, or it doesn't matter that much, because the drift speed is so small with any reasonable current, because this n number is really, really big. So we can do a quick calculation, right? Or we could do some thinking about it. Thinner sections of wire, cross-sectional area goes down, the drift speed goes up, and the current has to stay everywhere. Stay the same everywhere, because current is constant in a circuit, in a branch of a circuit. Right? So we can do a quick calculation. 1 millimeter diameter copper wire carrying 2 amps of current. We can do the calculation there, and you end up with about 0.68 meters in an hour. So you leave a light switch on carrying 2 amps of current, which is decently large amounts of current, not huge, but you're not going to trip a circuit breaker, but it's certainly there. And the electrons won't even move a meter through that wire in an hour. So there's one other piece, is this really only applies to DC current, like with batteries and that kind of thing. Household wires carry AC current, and AC current actually is a sinusoidal graph, like the current changes direction constantly. And so it doesn't actually drift, right? Over time, it just moves back and forth. The amount, I don't know if you can see that, but that's an A with a little like circle on top of it. That's a symbol for an angstrom, which is what, 10 to the negative 10th meters. So a typical AC lamp cord, they just vibrate back and forth by a distance of about 2,500 angstroms. So very, very little motion for those. We can do another calculation. This circuit contains wires of different thicknesses. Section 1 has a 2 millimeter radius. Section 2 has a 1 millimeter radius. By what factor does the drift speed change? And so we'll come back and answer that question. Another idea here is the idea of current density, which is amps per meter squared. And so this is a way of thinking about not just the current and not just the drift speed of individual electrons, but really thinking about how when current is flowing through a wire, we think our analogy is sort of water through a pipe. And we earlier had a discussion that generally, we say that the charge is on the outside of a conductor, and that's true for static situations where you charge something up and leave it alone. And actually, the current mostly travels on the outside of a wire when it's alternating current. But for direct current, for batteries hooked up to a wire, you do get this bulk charge flow through the wire. So we could talk about current density. And it can depend on the geometry of the wire. And so what you see here is a picture kind of showing that we have pretty uniform density for a straight section of wire. But then as it curves, the current density gets lower on the outside edge because it's got farther distance to travel, kind of more space. And it goes up at the kink kind of part of it where it's bent inward there as it goes. We can also talk about current density in its kind of generalized form. Current is sort of defined in terms of the integral of current density dotted with dA. So current density in some ways is a more fundamental idea, how much current per square meter, and then that would give us this is kind of starting from the molecular view and working our way up. So as the area decreases, so the current density increases to maintain that constant current. So another calculation we can do, a steady current flows through a wire with a circular cross-section of radius 2 millimeters. J is uniform throughout the wire, and 4 amps is the current. So if we're dealing with something constant where we don't need to do that integral, we can just say that current is current density times area. It's a pretty straightforward calculation. You can find that the current density is 3.2 times 10 to the 5th amps per meter squared. But we might say, well, what is the current if current density is not a uniform thing, if it depends on, the radius, how far out? And this is not uncommon either, that the current density is not actually constant through a conductor. This time you have to actually compute the integral. I can leave you to actually try doing this integral, but it's not that complicated, right? If you've got a dA, you're in a circular wire, then you need to sort of integrate from the middle out by doing circles, 2 pi r dr, and you can get that value. All right. Ohm's law again. 2 versions. Macroscopic, when we're dealing with circuits and circuit elements, V equals IR is generally how you see it. Units, joules per coulomb is, your voltage. Amps is our current, and ohms is the resistance. In the microscopic version, we actually don't talk about voltage. We talk about the electric field, because the electric field is the thing that causes the charges to move. And instead of current, we think of it in terms of current density, where we have newtons per coulomb for the electric field, amps per meter squared. And then that density thing, that's not, the rho isn't density here, it's resistivity, ohm meters. So that's our resistivity unit. We can also write it as this, Newton meters per coulomb, right, which would be joules, is amp per meter squared times ohms times meter squared. And you get the same basic relationship between these for Ohm's law, right? Looking good. So this one's on the AP equation sheet as well, a relationship between electric field and current density. In Unit 10, we'll talk a little bit more about kind of the electric field and electric potential relationship, because they are related in a predictable way. And hopefully it makes a little bit of sense as we go through it. So just a couple of things to look at, right? Resistivities of different materials here, right? A copper wire carries a current of uniform density. We have an electric field across it. What is the current density? So this is the other kind of thing you can say. You can say, well, I know the resistivity. If I know the electric field strength across it, I can talk about the current density. And then I could go from there to figure out the current as well. 7 times 10 to the 8th amps per meter squared. So that's kind of it. This is a little cartoon. And I like this because it's a volts trying to push current, right? So the voltage, the potential, is there to push charge around. And the resistance is the thing that's trying to restrict how fast current flows. And that's kind of our relationship that we talked about with Ohm's law.